Thank you. So hello, everybody from my side. I am Zamaan from Henkel, and I'm joining this talk with my colleague from AVL, Thomas. So I'm a manager of a team here called in Düsseldorf in our headquarters in Germany, called Engineering and Advanced Testing Team. And we want to take you today to our activities related to digital solution which can accelerate the battery design and development cycle. So I leave it to you, Thomas. You can have a few words about yourself also, and then we gradually start the talk.
Yeah, thanks very much. Yeah, hello also from my side. I'm based in North America, so I work for the Plymouth, Michigan office of AVL. Serve the North American market out of Tampa, Florida, and yeah, happy to guide you through the presentation today, also from the AVL side.
So I start gradually with a short introduction about our contribution to automotive industry. So Henkel is a material provider, and it partners closely with OEMs and tier 1 suppliers in automotive industry to deliver advanced material solutions that enhance performance, reliability, and manufacturing efficiency. So we see each other not only as a material provider, but also a solution provider. So Henkel supports customers from design to production, enabling innovation in electric vehicle battery systems in different ways. So since the headquarters is located in Düsseldorf, a little bit about our inspiration center in Düsseldorf, Germany. So it serves itself as a global hub for developing sustainable and effective solutions in adhesive sealants and functional coating, fostering close collaboration with customers across more than 800 industry segments. So, of course, with emphasizing on sustainability, so it features also the most resource-efficient design, equipped with advanced digital tools and data-driven laboratory to accelerate the product development cycles.
Yeah, and the overlap that we have with AVL is very briefly in 2023, we started a collaboration, a joint partnership between Henkel and AVL. And yeah, this is obviously continuing, but for those who don't know AVL, maybe very briefly, I can show a couple of facts here. On the next slide, actually. So we are a pretty old privately owned company in the automotive space, mainly. Nowadays, also a little bit more into aerospace and other areas, but predominantly we are for mobility technologies, and we offer engineering services, testing, hardware and testing solutions. And also we make our own in-house simulation software that we use internally, but also sell externally. It's a very R&D heavy company, privately owned, a large number of employees for such a private company. But yeah, overall, we are just globally represented. And specifically in the e-mobility space, we have now about 20 years of experience. If we move on to the next slide. Yeah, a long history in battery projects that we do for OEMs. So you've seen on the Henkel slide a good amount of customer logos, and there's a big overlap between Henkel customer and AVL customers. So overall, this makes sense to have such a partnership, but how this works out in detail, Zamaan will show now in the next couple of slides in more detail.
Thank you, Thomas, for take it over. So introduction to our digital solutions from Henkel's side. So why simulation in Henkel? And, everybody knows basically that the development of electric vehicle batteries on one side is facing with customer requests, like longer range, cover range in the batteries, faster charging, improve safety aspects, and etc. On the other hand, you have design trends, for example, like this achievement to the higher energy density, and of course, focusing on sustainability. So all in all, it's targeting Henkel, and we need to offer solutions. And on the other hand, the reality is that the development cycle is still very, very long, considering changing of the trends on a regular basis and meeting the customer requirements. So that's why Henkel is offering digital solutions to overcome these challenges. So over the last 3 years, we built up a team here in Düsseldorf, which is related to simulation and modeling for different disciplines in electric vehicle batteries. So when we talk about simulation in Henkel, basically we talk about a kind of ecosystem which has been developed over the last 20 years in Henkel. So different SBUs are offering different simulation supports to our customers. It can be from very simple support like providing material cart, or it could be in some of our sub-business units in connection with OEMs. They are highly integrated to optimization process, and they basically offer the design, optimized design. So that was also the motivation for us to get involved in the e-mobility over the last 3 years. And as you can see, the digital solutions of Henkel incorporate so far 3 different disciplines: thermal management, structural performance, and last but not least, application. When we talk about offering these digital solutions, we were following 2 different objectives. At the first time, basically the idea was from the beginning how to integrate the performance of our material in the efficiency of the battery systems in either of these disciplines. And in order to be able to develop some concepts like digital twins, so we had to build up some also experimental infrastructures here in Düsseldorf. And the other important reasons for us was basically to have a one-to-one technical discussion with our customers. So we wanted to also to reach to this level of technical discussions, to have really more fruitful meetings with the customer, understand their needs, and accommodate the requirements as soon as possible in a very efficient way. So thermal management system is basically incorporating the effect of our material in the performance of the thermal systems in the electric vehicle batteries. The structural performance is basically incorporating the structural efficiency of the battery systems under different loading scenarios, basically the ability of the battery system to maintain form and its functions under different loading scenarios like crash, and etc. And more important topic when it comes to the end, when the product is supposed to be dispensed in the production line, is the application. How can one basically achieve to a more efficient application process? And in the next couple of slides, I will show you the solutions that we can provide to our customers in order to accelerate the design process in the design centers when it comes to the development of batteries. Of course, when you want to achieve to this level of capability, you need to have a workflow. And you can see here, this workflow can be divided to 2 different parts. The first level is the material level itself, which includes testing, modeling, and validation. And of course, the second part, as you can see, the battery level, that I come to that in a second. So when we talk about the material level, it's incorporates 3 different topics here, as you see. The testing part is nothing except the material characterization measurement. So that means the determination of mechanical properties or thermal properties or rheological properties under different scenarios. For example, when I talk about mechanical properties, so we have a really different range of loading scenarios that the battery system is supposed to be undertaken, like a static load vibration, for example, fatigue load, and in crash scenarios, for example, when the battery system is experiencing accident. And later, fatigue, for example, when a component is supposed to go under millions of cycles, and it's supposed to still keep this functionality, you know, on one side, if you imagine, for example, a thermal conductive adhesive, on one side, this product is supposed to bring, of course, thermal management, and on the other side, brings a structure integrity to the system. So all in all, they needs to be characterized and basically determined through testing. So here in Henkel, we have a large infrastructure here. It can target different loading scenarios from static to fatigue loading, like crash scenarios, high velocity test, and it goes to thermal characterization, direction, also rheological for the squeeze flow modeling, and etc. At the same time, you need to have a concept for modeling for any of materials. For example, modeling a foam as a potting in cylindrical battery pack is really different from modeling a structural adhesive, or a sealant material is totally different from the other two materials. So it's very important to have a concept for either of the materials. And based on this concept, you arrange the corresponding testing campaign. And at the end, when you merge these two columns with each other, testing and modeling concepts, you come to the validation. And this is exactly the stage that you have created a data card for your product, and you can leave it to the customer, and the customer can proceed with the simulation for different disciplines. The battery level is also another part of this workflow. So that was very important for us to develop the battery packs that we can use and integrate or materials that we offer or develop in the e-mobility portfolio at Henkel. So that was basically the motivation for us to develop Henkel digital battery pack. And you see here in this picture, two versions of that. So in the left side, you see the version with prismatic cells, and in the right side, you see the other version of the Henkel digital battery pack with cylindrical cells. There are, of course, other different versions with different dimensions, different functionality, different cell geometry, and etc. But as I said, the motivation was just to integrate our e-mobility material and check the functionality of either of these materials under different thermal and loading scenarios. So testing with batteries, that was also another part of this workflow that at the beginning, over the last years, so we used to get the support of our external partners particularly for thermal management system simulation. So we worked with prestigious institutes in Germany. And later, with the help of AVL, we developed the battery test center here that I take you through the specification of this center in few seconds. And right now we are capable of doing experimental tests when it comes to thermal management systems and effectiveness of our material for thermal scenarios. And of course, by having this digital capability, which is developed for different battery pack designs, so you can implement from time to time different loading scenarios, different use cases, and examine the effectiveness of the performance of the material on different scenarios.
Yeah, thanks, Zamaan. So as you saw, basically on the left side, you really had the material expertise, and this is the core expertise, obviously, of Henkel. Here, AVL, that's not our domain, but really, where is our domain coming from the vehicle? If you're there down to the back or going into the cell level, here's where AVL can help and contribute. And specifically for the test center, also we contributed with test equipment. So AVL makes cyclers, for example, in-house, makes test chambers in-house, and also is building up test facilities. This can be containerized solutions or also customized. So test equipment, heavy, but on the engineering side, also our core expertise is what we do day to day with the OEMs, develop and research pack designs, cell strategies, for example, operating strategies, and so on. So there's a big battery expertise in AVL that we can now pair with the material expertise at Henkel. And yeah, one thing where this really comes together is in the digital part, where we have simulation software that is developed in-house at AVL that we also sell externally. So we see two tools here, and on the next slide we see a big, yeah, let's say suite of tools that we can use in our engineering realms. But I want to point out for today 3 tools that you will see throughout the presentation that are also used at Henkel. So the first one would be AVL Cruise M. This is a multi-physics simulation tool that's really used a lot in the pack design or for the thermal strategies, a fast running tool that can really do a lot of case studies as it is much faster in real time. On the safety side, we use 3D CFD. So especially where, for example, it comes to thermal runaway events or venting gases, classic CFD is the tool of choice for AVL, and we developed our own code for that. And finally, I want to point out Prion Lab, which we use on the application base. So later on, you will see some examples of what you can do with this kind of like new technology CFD, which is meshless and is very easy to use. Yeah, so maybe Zamaan, let's look into some of the use cases.
Thank you. So I take you in the next coming slides to different topics, as I previously mentioned, that we can offer in a part of our digital solution. So we start with battery thermal management. So I'm very happy to introduce you to our battery test center here in Düsseldorf, in our headquarters in Germany. So the battery center test center was fully operational since last September in 2024, and it's very important to know that the key advantage that Henkel in this battery center offers to its customer is the creating a digital twin of each battery, applying Henkel's materials, advanced materials, and using digital material levels in order to simulate different scenarios and then validate the results in the real system. So in this way, the Henkel digital twin basically offers the performance of our materials in evaluating impact on the fast charging performance, for example, heat transfer and temperature distribution and different thermal management concepts. It has, of course, different specification in cooperation with AVL. The test bed is Puma, which is provided by AVL, integrated in a climate chamber. The climate chamber is capable of different charging scenario, fast charging, discharging up to 270 kilowatts, and with different ranges of environmental simulation in the climate chamber, for example, from -40 to +90 degrees, and of course, relative humidity from 10 to 95%. And of course, in addition to that, active coolant condition, different cooling scenario can be implemented in this battery test center. And of course, last but not least, the battery leakage test is also equipped in this battery test center in order to also investigate these aspects in the electric battery systems. So I take you a little bit in the next coming slides to the topic. So this digital twin is supposed to go to different levels. So in fact, during these different levels, which is depicted here, we can simply examine the performance of our material in the effectiveness of the battery pack for module level, pack level, and integration with, for example, vehicle thermal management systems. And at the end, it is also in our roadmap to integrate the full vehicle, including complete system control and validating the vehicle drive cycle performance analysis in this whole digital twin. So it means that if I go, for example, to module level, so we are able, starting from a very simple element in the battery pack, which is the cell itself, including different chemistry of cell, different size, different geometries. And then integrated to the module level and then checking the performance of material. For example, when we talk about a team layer between the cell and the cooling plate, so it can be demonstrated what kind of influences it brings when the thickness of the team layer or the thermal conductivity of the team layer is changed. And of course, when you add to the pack level, it goes to the greater extent. And the intention, as I explained, is supposed to integrate also the vehicle level system. So all of these activities, of course, is being done in Düsseldorf with a strong partnership with AVL. Thomas mentioned about AVL Cruise M, and I mentioned already about the battery test center integrating this Puma test bed, and I asked Thomas also to take you a little bit more about the digital twin concept and how AVL can contribute in this roadmap.
Yeah, thanks, Zamaan. So from the simulation software perspective, we want to provide the digital twin respective accuracy for each level. So, and it even starts at the cell level. It kind of like one layer deeper than what was on the previous slide. We of course need to know the cell. So this is the basis for the thermal investigation. It will create the necessary, or it will provide the heat that is generated by the cell throughout the operation. And the software can help here by providing a cell library in different degrees. So this can be RC models, or this can be electrochemical models of really high accuracy. So the AVL software can help here in various ways. But then when you move on to the module level, you really can investigate and build a digital twin on the module level. And once you've validated basically your materials, this allows you then to very quickly try out new combinations, try out different concepts. So you can do this much faster than with real prototyping. And here the software really helps you. So that's mainly done in Cruise M, I would say. And moving on to the pack level, still you build your pack, you build your cooling strategy, maybe experiment with different cooling platforms, like let's say bottom cooling or serpentine cooling. And you want to understand the thermal behavior of it together. You can model the pack in a coarse 3D here already. So this allows you also to already see the implication of the various material and cell choices based on their cooling concept. And yeah, moving on then in the end to the full vehicle, the software here can support by providing, for example, validated vehicle models. So thanks to AVL's benchmarking, we have access to basically already validated models of real vehicles. We see here the Hyundai Ioniq 5. There's also a Tesla Model 3 or Model Y, for example, ready available. And so therefore you don't need to purchase a vehicle or have a real prototype. You can just, let's say, test a different concept and see the implication on the real vehicle. So this is all faster than real time. So this is at the bottom, Cruise M, basically. If you want to go in very high detail on the module or the pack, we also can use 3D CFD. So let's say if you're already looking very much in the details of the cooling channels or the exact design of the module, also here you can already use simulation before you build your real prototype. But yeah, overall, it allows you to save a lot of time. And I think we will see a case study from directly from Henkel on materials choices by Zamaan now.
Thank you, Thomas. So in the next two slides, I take you to two different use cases that we have work on it. And it's, of course, in a module level in both of them. So as you can see here, it's one of the module levels that we have work on the cylindrical cells integrated with our potting materials, and underneath of the battery cells we have used the TCA. So it's a very simple DOE just to demonstrate the effective of our material in combination with simulation, and how can you benefit from simulation in order to find the bottlenecks in the design process. So you see that here I have different thermal conductivity for my TCA layer here between the cooling plate and the cylindrical cell. And in addition to that, I have also different scenarios for cooling and also charging, fast charging, and also normal charging. And you see that here simply you can see in combination of either of these load cases and thermal conductivity and also potting material, you can simply find that which combination in which situation loading scenario can lead to more effective and efficient way, which is here in this case is controlling the temperature, which is raised in the cylindrical cells. So I go for more level, which is a kind of digital twin that we developed 1.5 years ago. So you see here the simulation of a module level again from a prismatic cell concept. And then here you see that I have a load profile with state of the charge, which is starting from nearly 50%. And then it is increased to around 80%, and the state of the charge after that, it again starts to be decreased, and then again after that, as you can see, it raised to reach around again 50%. So look at for this simulation results, which was kind of combination of STD and transient state of the full cycle, which took about, consider about 2 hours and 45 minutes of this simulation. And you see that my cell temperature is really changing when it comes to the upper level of a state of the charge, around 80%. And after that, when it decreases, the cell temperature also decreases. And again, after the ending phase, which is reached again to nearly 50%, you see again the increase of the temperature. But what is important for us, the integration of this to the team layer here between the cooling plate and the cell. So you see that the team layer changes when the state of the charge increases. And then after that relaxation, the temperature decrease also happens in the thermally conductive adhesive layer between this cooling plate and cylindrical cells. So that simply help us to come up with the bottleneck designs in this scenario, and we can have a better understanding about the thermal conductivity, which is really suitable for this loading scenario, and the corresponding thickness for this team layer.
Yeah, obviously, I mean, the understanding the thermal management of the thermal part in normal operation is important, but especially where simulation is very helpful is when you look into hazardous events. So you can take it even one level beyond and start to look into thermal runaway events, for example. And here you can do it more or less safely on the computer before you start any experience really too much already. And in the software we can cover a wide range of effects already, starting at the cell level effects, where we simulate the cell heat release based on different chemistry types and different cell geometries, for example. So there are different methods in the tool that you can start with very limited data. Ideally, you have already measurement data that you can characterize this a bit. But then going really also throughout towards venting and particle ejection to simulate flammability and combustion of the venting gas. We can simulate arcing, melting of barriers, for example, and also the simulation of bursts. So these effects then are more important on the pack level, where the hot venting gas might flow differently depending on how the back design is, and especially also when back deformation is coming into place. So on the bottom right here, you see some ejection of hot venting gases here. So the simulation really for a very low cost compared to blowing up real packs, and basically you want to only blow up a real pack ideally once at the end on the validation side, can save you a lot of time and cost. And we can really simulate now, thanks to the speed of the tools that they've reached in the last couple of years, up to something like 200 million computational cells, a really large pack, within a matter of a couple of days in full 3D CFD. So this will be a huge next step to make safer packs, and especially also making sure that the materials that were chosen for the optimal thermal design in the previous step are also actually safe in the hazardous event.
you.
But
So I take
yeah.
you.
Yeah, go ahead with the structural.
Sure. Thank you very much, Thomas. So I take you for the second topic to the structural analysis. So as you know, the function of the materials that has been used in the electric battery pack, so it's under a structural analysis, is supposed to maintain the form and functionality, as I mentioned earlier. So you see that here in this slide, typical load cases that in the design of the battery pack, when it comes to mechanical loading, is mainly important to be addressed, like crash, for example, or shock simulation, drop test, and crush simulation. So I take you in the next slide a little bit more to integrating this concept, the effectiveness of the material that we provide to the customer in order to increase the structural integrity performance. So here I have again a digital battery pack from Henkel, which is this time a prismatic cell. And you can see that in this concept between the prismatic cell and the cooling plate, I have used our thermally conductive adhesive, which covers different thermally conductive values. Between the cells, for example, I have used the compression pads, which was also offered by Henkel. And in the, for example, cover between the lid and the frame of the battery itself can be also used sealant, MS polymers, for example. So let's have a look to the typical loading scenarios that needs to be addressed when you want to design the battery under structural performances. So you see that crash, drop test, modal analysis even, which is a simpler mechanical analysis dealing with vibration and bending and torsional stiffness measurement. And of course, for all of them, you have the corresponding norms and standards. So in this particular case, we want to take you in the next sample to the crush load scenario. So the crush is basically happening when the car is experiencing accident, but the battery is not influenced directly, but the pillars or the other components are basically being forced to compress the battery pack itself. So it means that in this case, in crush loading scenario, the battery is experiencing a kind of a static load around 100 kilonewton, 120, depending on the design concept. Every customer has different values, but basically the loading is applied on a pole on one side of the battery, and the battery is supposed to keep its structural integrity. In this case, in this particular example, the battery cells are not allowed to have more than 10% of debonding after this induction of the load. So you see the load case, crush simulation, side pull, and as I mentioned, that the side pull is pressing the side of the battery on one side. On the left side, you see that the solution Henkel can provide as a material provider for thermally conductive adhesive can be used between the cells and the cooling plate. So we mentioned earlier, so this particular team layer has the functionality on one side, bring the thermal management concept to the battery pack, and on the other side, which is more important, should keep still the integrity between the cells and the cooling plate under different loading. So it could be only vibration, and it goes to these loading scenarios. It could be even more severe when it's combined for crash loading. Imagine, for example, implementing inertia in different directions with very high level. So you see that in this case, I can offer my customer a great variety of thermally conductive adhesive with different strengths. For example, here you can see that the range of the lab shear is from nearly 2 megapascal to 10 megapascal, which is a very big value, higher strengths, 10 megapascal for a thermally conductive adhesive, which is filled with fillers and bring thermal conductivity to the system. And you see the corresponding mechanical properties in this particular case, because we want to model the debonding phenomena. So we are dealing with more sophisticated and advanced mechanical properties like fracture inertia. So you see that among this range that I can offer to the customer has basically this possibility to integrate the lightweight design and goes for the design optimization. Here you see that with TCAA, which is the weakest adhesive layer, of course, if they want to use this TCAA layer. So the design in the upper part, as you can see, that the side beam is basically heavier, TCAA and TCAB both filling the requirement, which is defined for crush test scenario, not having more than 10% of cell contact area debonding. But when you change to TCAB and a lot of other range, which is still able to address the capability of fulfilling the requirement for this norm, you can go to the design optimization. Here you see that with the right selection of the adhesive, I can save the weight here up to 35%. You know, I keep the profile thickness the same, but as you can see with the reduction of one part in the side beam, I can massively save the weight of the battery pack. And this is exactly the way that the simulation coupled with the experimental validation can accelerate the battery design process.
Yeah, speaking about the experimental validation, how AVL can support Henkel here is with test equipment. So we, besides the cell cyclers, we offer test chambers, so thermal chambers, but specifically also shaker attachments for the thermal chamber that you can investigate the vibrational behavior also on the testing side. From a simulation perspective, the tools, the finite element tools and structural investigation tools that are out there in the marketplace are really doing a great job. So there's no need for AVL to develop an in-house tool here. We support with methodology and making the best use out of these tools in combination with the test beds. So yeah, any testing need, we can definitely support here, and also any engineering methodology.
Thank you, Thomas. I take you to the last discipline that I wanted to introduce you today. So it's the material application. So basically, when we talk about application of our materials in the production line, so you know that the manufacturers are basically facing increasing pressure to ensure the reliability and performance of the battery assembly, because you know, it's very important. It's a very challenging task for the manufacturers basically to apply precise forces during the material applications, because on one side, this precise forcing guarantee that the material is applied on a very even thickness, and also there is no void involved. So a way to guarantee that the thermal management is working very good. But on the other side, this precise force, if it is not addressed on a very correct way, so it damages the other parts, the other components. For example, in the examples that we discussed today, so if the force is applied by the robots during the implementation of the battery cells on the adhesive layer, which is basically supposed to lie around above the cooling plate, is not addressed on a correct way, is not estimated correctly. So basically we are damaging the cooling plate underneath and bringing more problems for the performance of the whole battery pack. So it's very, very important. And basically it's a very challenging question when it comes to the application. And here also, it's also another discipline that we can support our customers by simulation and digital solutions that we can offer. So Thomas will take you a little bit about AVL point of view.
Yes, absolutely. So this is a really interesting use case that came up during the recent years. If we look at on the left side here, we see a module, and yeah, just a cross section of the module. And if you look at the bottom, this slight blue line here on the module is really bonding the module to the cooling plate. And now we can use a tool like Prion Lab that models these viscous materials very, very well. It does it so by splitting the material into small little balls, basically. And the technical term behind it is SPH, so smooth particle hydrodynamics. And this allows to simulate such materials very well. If you look at the bottom video, you see how it is applied, how the module is pressured down, and how it spreads really. And the tool also allows you to get the shear stresses and forces out of it nicely. So one of the greatest advantages is that you visualize it really well. So you see immediately if the material application is spread perfectly, or if you have any gaps or voids, which would be very negative on the thermal heat transfer and conductivity. But the most important thing I think about this process or workflow is that it doesn't require any meshing. So what you can do is really just take a CAD model and apply it on the pastes, and within a matter of hours of simulation time, really then get this distribution. So you really can run case studies with different designs and also different materials, and choose your right application pattern and also the right application strength before you do any a lot of real life prototyping. So again, saving cost, and especially you want to minimize the amount of material you apply, because in the end it's cost that ends up in the final vehicle that we want to drive the cost down. And Zamaan, you can give us already some concrete examples how it's used at Henkel.
Yeah, and in order to be able to offer this solution to the customer and support them for application process, so you need to again follow a workflow, and you see that the workflow in Henkel is including again experiment, modeling, and simulation, and at the end validation. So of course, in this way, we also cooperating with AVL. I come to that in a second, but in the experiment here, so I introduced you to Battery Test Center, which was launched last year. But in August 2023, we opened the Battery Application Center, as you can see here in this picture. So it focuses on the practical application of our materials, Henkel materials, including adhesives, sealants, thermal interface materials, basically to full-scale battery systems. As you can see that the battery here is on top of this table, which is supposed to be used for dispensing different types of the material which is being used in the pack design. So basically, these robots with this functionality that they can bring, it features the automated dispensing systems that is supposed to replicate the production environments, allowing to have more efficient assembly and disassembly processes. So that was one part of our experimental when it comes to dispensing and modeling this flow behavior, which we call it a squeeze flow modeling. But the other one, as a part of any material card creation, so we need to also have a good experimental setup for material characterization, which is in this case rheological characterization. So we have a very good facilities here in Henkel and the corresponding know-how for it, how to characterize the material, which leads us, based on these experimental inputs, we are able to create the data card, which is basically the second part, modeling and simulation. We create the data card based on the experimental test campaign that we arrange for flow behavior of any materials, and then we combine it with the modeling concept. So depending on the solvers that our customers are using, of course, the material concept can be different, but we can address any types of material models with the know-how that we have in Henkel. And of course, when it comes to simulating and validation part, it is basically the incorporation with AVL, for example. This particle-based software, Prion Lab, is being also used by Henkel as one of the software solutions that we are using for this topic. And at the end, the validation happens. So in this stage, we can provide to the customer the material data card, and they can simply integrate it in the simulation, and they can model the process and get the corresponding load, and they can come up with the most optimized dispensing pattern and have more reliable and efficient application process. So we had a very interesting talk today. We take you a little bit to the outlook that we have planned in this regard in cooperation with AVL. So as Thomas, my colleague, right at the beginning of this talk mentioned, so we have started this collaboration with AVL, the partnership, in 2023. So at the beginning was the idea how to make this acquisition of the battery test bed in order to create the Henkel Battery Test Center. And afterwards, in 2024, after we got basically the opening of this building and having the battery pack test bed in connection with the software Puma, we also expanded the other cooperation with the AVL in the meantime. So using the softwares that Thomas took you a little bit to the functionality of either of the softwares, we are also using in our daily simulation activities AVL softwares like CruiseM for our Henkel simulation, for example, thermal management systems, and particularly for developing digital twin of the battery in different levels. And in the meantime, we got also this opportunity to create the Henkel library in CruiseM. So that means that the customers can simply go to CruiseM and they have the access right now to Henkel material library. They can take whatever which is available in the Henkel e-mobility portfolio as thermal solution, and they can basically use this material, and the corresponding material properties is also integrated, and they can start the simulation. And then when they are happy and satisfied, they can order simply the material. And for further supports also, there is the contact address of our corresponding simulation engineers is attached to this library, and they can also ask for further supports. So what's happening in 2025, and after that, I will hand over to Thomas.
Yeah, thanks, Zamaan. So obviously, we will continue this in 2025 and beyond. So one of the major milestones for this year is that we go up to the vehicle level at Henkel. So we will have a validated vehicle model available, which then also shall prove the superiority of the Henkel materials on the vehicle level. Apply this for rapid prototyping. We will obviously continue to add more material cards even to the software. And also a big part is that we roll out this process or this simulation capability global at Henkel. So we started to work with the Henkel North America team together to bring this also to North America. And in 2026, we will then even continue deeper, going stronger into the AVL topics. So there's the topics with FireM, for example, also addressing and starting to address battery aging topics much more, and even expanding more globally, as Henkel is very global. It's going into different markets. So yeah, all in all, very excited about this partnership. And thanks, Zamaan, for the talk today and for including me today.
Thank you very much, Thomas, for your nice presentation and cooperation over this talk. So after that, we basically reached to the end of our session today. Thank you again very much for your interest in our talk. And I don't know how many minutes is left for questions.
Yeah, I think we're already over time. So we got a reminder by Volta to wrap it up. Thanks for staying so long. From my side, I can stay a little bit longer. So if there's any questions, you can just address them, or you also can reach out through our email or LinkedIn for either a copy of the slides, or just if you want to connect in the one or the other way, we're more than happy to do so. And if anybody has questions, maybe just please a quick introduction from your end, and yeah, feel free to.
So you can see the questions. There are some questions in the chat.
They will end the forum in 3 minutes. So there are 3
Oh.
quick minutes for any urgent questions. Otherwise, we have to follow up offline.
But anyway, I put my, the email address of both of us. So you can reach us through email addresses here in either Henkel or AVL. For either of these disciplines that I showed you, it goes to at least 30, 40 slides of, a slide deck, and it goes to different use cases, loading scenarios. And if you're interested, we can, of course, have a longer session in order to investigate how can we support you through these digital solutions that we can offer.
Yeah, I think it was a long day for everybody. At least I think it's late in Europe. It's maybe already a long presentation also, and morning on the West Coast. So yeah, I think since there are no
very comprehensive presentation, so I don't have any questions right now. I'm just trying to absorb it all.
Perfect. No, thanks for the feedback. I hope it was of interest to a lot of you, and I think pretty much everybody stayed till the end. So I think that's a good indication that we at least provided some overview. As Zamaan mentioned, it can go into much more detail, but yeah.
Anyway, thank you very much from my side for having us today in this session, and looking forward for future exchange with you.
Yeah, thanks, Zamaan. Thanks, everybody. I would say we close.